Okay, so I want to go over the stuff from section 1.8. This will kind of finish this up for this section. And here's basically what I want to talk about for section 1.8. It says algebra of functions and function composition. I want to summarize this as this one statement. Building functions from other functions, building new functions from other functions. Okay. So we're going to start out with a couple of functions, and then we're going to build new functions from those. So we're just going to do, what can we do? We can add two functions. We've done this in basic algebra when we're just putting together things. We can subtract one function from the other. I can multiply, I can divide, and finally I can do this thing called composition. And this is the symbol. I'm going to do that as a big circle. Okay, it's not a dot like the multiplication, it's a big circle, and this thing is called composition. So that's what the algebra of functions and function composition, how to build it, what does it look like, you know, when I tell you here's some functions and then do this addition, do this subtraction, I don't want to do this in a word problem. I want to specify, you know, here's some symbology for it, and then you just understand how to do it. Okay. So that's where we're going through with this. Let me kind of slide this over because it likes to be up top. So perform operations on functions, evaluate a difference quotient. That's kind of a form of building these things. So finally, we're going to do a difference quotient. And the difference quotient is the average rate of change, that arc, average rate of change. You remember that stuff? Y2 minus Y1, X2 minus X1. But this is going to be a little differently, and then I'm not going to specify a couple of points. I'm going to build a new function from these other functions that's going to represent what the arc is, but you have to later come back and say, here are the points that I want it from. Give me the X1 and then, you know, calculate this thing for me. Okay. So that's what we're going to do today. First ones, here is the definitions, okay, of what I just said. Okay, so I'm given some function f of x. So let's start with just 2x, some basic function. And then g of x is equal to x squared. Okay, so I've got two different functions. Here's John, here's Henry. That's what these different names, f of x, one thing, John is 2x, Henry is x squared, okay? And so here's the directions, and it will say something like form the new function f plus g of x, which looks kind of strange. Because I've said never kind of split these things up, you can't divide, but this is again a new name. Okay, so, you know, Tom, Henry, Jack. So what this means when you see this though, it means to add f of x and g of x. Add those two functions. And the way the mathematic definition, the shorthand, so mathematics has a lot of shorthand where that you don't want to spell out all of these things long, you just want to learn the shorthand and then you know what it's telling you. The shorthand, it says when I want to form f plus g of x, a new function, I'm going to add these functions. So here's your cookbook. Form this, well, what do I need to do? Oh, that's just f of x plus g of x. So for this, in our example land, I would go through, I would find this, that would be 2x plus x squared, and I kind of want to put parentheses are all around here because if this is a negative, I've got to distribute my negative across, okay? So let me change this a little bit so we'll have, let's go plus 1 minus 1, okay? So if I did this one, this would be 2x plus 1 plus x squared minus 1. Positive, positive, I get to drop this thing. So this would look like 2x x squared from this one, plus 2x from that one, and then plus 1 minus 1, that would just be 0. So that would what the new function from two old functions look like. New functions from old. Okay. How about if I want to form this next one to the left, f minus g, the difference of two functions, f minus g of x. This is defined as, this is kind of like a three-line number. Sometimes you see this as defined as, but it is equal to take f of x, the first one, and subtract the second one. Okay. So when I'm doing this, I say, here's the definition. I can go directly, but I like putting this in because the next step, I'm going to put these in parentheses and say, what's my f of x, what's my g of x? So that way I can be careful to distribute that negative as needed. Okay, but I do it with the plus, I do it with the multiplication, I do everything there. So it just gives me into that habit of putting everything and making it correct. Okay, so here's my f of x. That would be the 2x plus 1. My minus my g of x, all of this stuff, minus x squared minus 1. And again, I put this in there. So if I'm multiplying, I distribute. If it's plus, I just drop it. That's the most simpling. But here, I'm going to do the subtraction. So I've got, this is understood plus 2x plus 1 minus x squared, minus and a minus gives me plus 1. And then I can re-simplify. This is plus 2. Minus x squared from this distribute, 2x plus 1 because I had to change that. And that one's a plus 2. So that's the difference of two functions. Let's do the product of two functions. Now this is just a dot. Okay, so later on we're going to do a big circle in here and it's going to be something totally different. Okay, and I have to be careful whether this is not f circle g of x. This is f dot x, f times g. This is composed, this is composition, f circle g. Okay, we'll do that one later. So to form this new function from these two old, I just want to take f of x, and we'll put these in this extra parentheses, times g of x. That's what that means, f of x times g of x. Or just simply the f of x times g of x. So for my example, it says take all of f of x, 2x plus 1. That's why I want that parentheses, because all of this gets multiplied by all of my g of x, x squared minus 1. Okay, so in some cases, this is all I would need, right? I've got them in factored form. Here's a factor, here's a factor. In fact, I could factor that. And factors are always nice, or sometimes I just need to do the expand. So if I expand, okay, I would do distribute, 2x times x squared, 2x cubed, and then 2x times negative 1 minus 2x. I finish that, and then I go to the next one and start distributing. 1 times x squared is plus x squared, plus 1. Plus 1 times negative 1 is negative 1. And then I simplify the best I can. And standard form would be, count these things down. 2x cubed plus x squared minus 2x minus 1. And that's what the product would be, the product of two functions. Forming a new function from two old functions. Okay. Sometimes this just helps you visualize. If I've got this thing, remember the zero rule, you know, I could kind of picture this as a multiplication function where this is 0, this is 0, this thing is going to be a 0. Or I just want to kind of graph these things together. So that's the product. And then again, we have the quotient. So the quotient looks like f over g of x. So this looks more like something, give me the value of x to evaluate it. So I could do things, again, all of these I could have done this. And this would be form the function f over g and then evaluate it at x equal to 2. Okay, but first we have to form it. And how do we form it? By definition, over here to your left is equal to f of x, g of x, with domain g of x not equal to 0. G of x can't be equal to 0 or that results in a division by 0. And we've seen that in the past. We can't do that. Okay, that's not defined. Okay, so for our example, we would do f of x, all of f of x, 2x plus 1, divided by the bottom, g of x. I was on a roll. Okay, so that's what this new function from old is. Now we got to be careful because I've got to make sure g of x doesn't equal to 0. And I need to pull out these numbers. And we've done this in the past with natural domain. So where is x squared minus 1 equal to 0? Well, I need to factor. In this case, I can. That's just the difference of two squares. And then my 0 property says, well, where's x minus 1 equal to 0? Where's x plus 1 equal to 0? X equal to 1. X equal to negative 1. And how do I pull that out of a domain? Negative infinity. Here's my first one from left to right. I get negative 1. I can't include it, but once I jump over, I go all the way up to my next one. I can't include that. That's the open parentheses. And then union 1 to infinity. Okay, so that's how I pull out the domain problems. This is my problem area. I used to call them my problem kids. I have to go through the functions and pull out problem kids. Okay. So let's go through, let's kind of work on some of these and see if we can pick up definitions, what do they mean, and how we do, okay? So there's some mixture of review in here, and then there's some other stuff as well. So let's go through our general function review and evaluating functions. So I'm given these three things. Here's my f of x definition. This is f of x. This is like Tom. This is Jerry. This is Harry, right? These are the names. I don't want to split these things up other than when I kind of form these things and then it's a new name that I don't split. So evaluate the function if possible. What does f of negative 3 mean? So if f of x was x squared minus 3x plus 1, my review is f of negative 3, the value of the function when x is negative 3, f of 3, negative 3 squared minus 3 times negative 3 plus 1. Negative 3 squared, that's 9, plus 9, plus 1, 18 plus 1, 19. That's what f of negative 3 would be. What is g of x? Oh, that's the big middle guy. That's just the square root of 8 minus x. Not to evaluate, I'm waiting for the x values or just a whole graph of things, right? This is actually split this way. What does f at a plus 1 mean? What is the value? Evaluate the function when x is equal to a plus 1. Okay, so identify, well, which function am I doing? That's the f. I want to write this out with parentheses because everywhere I have an x, I'm switching with the parentheses in preparation for putting whatever that needs to go into here. Whatever I need to evaluate. And later on, when we do that difference quotient, I told you we're going to do the average rate of change and come up with a function. That's what I want to do, is put whatever's in here into there. So this is going to be a plus 1. minus 3 times 8 plus 1. And if I need to fully evaluate this thing, and we're going to have to do this later on, so let me go ahead and kind of get used to this. Square this, so I'm going to square the first, multiply the two together the way I always do my square. 1 times a is 1a times 2 is 2a, and then square the last is plus 1. That's my standard way. Square the first, 2 together and doubled, that's the 2, and then square this. And then here I've got a negative and a distribute, minus 3a minus 3 plus 1, and then I would simplify. Grouping all my a squares, grouping all my a's, so 2a and a minus 3 as a minus a. That goes out, that goes out, that goes out, and then I've just got these constants to do. Plus 1 and plus 1 is 2. Negative 3 plus 2 is my minus 1. And that is in terms of a. So then I would just be waiting around for what my a is. Okay. What does g of 10 look like? What is the value of the function g when x is equal to 10? G of 10, g at 10. Is that. Here's my 8 minus x, and this is evaluated for x is equal to 10. Square root of negative 2. If I'm talking about real functions, does not exist. D and E for reals. Or if I'm talking about complex functions, this would be the square root of 2i for complex functions. Okay. And you have to know which one we're doing. Normally, we're talking about real functions and the pre-calculus calculus that we're doing, other than we recognize when we have complex roots. Okay. Okay. And then I'm going to go back over here and let's go to the next slide. And here we've got some of these definitions that we talked about. So we want to form new functions or evaluate them. Here's I'm going to evaluate. I've got to form the function and then evaluate these in terms of that x. Since they're both in terms of x, we're going to do whatever it says and then do. Okay. Now, here's what you can also do. Also consider this. If I do this, if I do f of minus 8 and I subtract off g of minus 8, that's going to give me the very same thing if I do f minus g of negative 8. Okay, so if these were graphs, if these were just graphs and I had to go get these numbers from the graph, when I did this and said what this is, I would go grab the number from the graph, go grab the number from the graph and subtract the two. Okay, so I really didn't have to form this stuff from here, but I'm going to go through, I'm going to say what is f minus g, wait for the x, and then use that to evaluate at negative 8. Okay, so what does this thing say? It says, and I always like to write this out, it tells me to go get f of x and then subtract g of x. Subtract g of x. What is my f of x? That's over there on the example. So that would be x squared minus 3x plus 1. Okay, and then we'll do a minus. That minus, and then my g of x, I go find that, and that just turns out to be 8 minus x. Okay, and this is, again, this is the function f minus g of x. Okay. Give me the x that you want to evaluate it up. So if I have several different values, I just plug them in. But the particular one they're asking for is to evaluate this at negative 8. And then I would just go through everywhere I saw an x, I replaced it with that. Okay, and there's, whoops, I got to be careful here, minus the parentheses, and that's a negative 8. So again, those parentheses will save you, and you just don't put that in there and make that mistake, okay? Because we want to evaluate this egg at negative 8, so that's a negative 8. And then we just do 64 plus 24 plus 1 minus the square root of 16, 89 minus 4, the square root, and then that would be 85. And again, if I did this, evaluated the f function at negative 8, and then I subtract this off from the negative 8, that gives me it should give me the very same thing, okay? It says, for number 6, it says evaluate g dot h at 0, the product of g and h, evaluate it when x is equal to 0. Well, what is g dot h of x look like? Okay, I could do this g of 0 times h of 0. It would work out to be the same thing, but I want to build this function first and then evaluate that function. Okay, I want to do this once and then put any number I want to in there. I don't want to kind of do all of this, simplify as much as I can, so hopefully save me some work. So what does this mean? G of x times h of x. G times h would be that. So now I'm going to multiply those. Give me my g of x, so I go over, well, that's the square root of 8 minus x. And then my h of x is 2 over x plus 1 from over here. Okay, and in this case, there's not a whole lot of simplifying. I can rewrite this a little bit. 2 times the square root of 8 minus x all over my x plus 1. Okay, there's not much else I can do in there. So now if I wanted to evaluate g dot h, this is g dot h of x. Depends on what x that the value is going to be. And now I'm saying evaluate at 0, it is 2 square root of 8 minus 0 over 0 plus 1 is 1. So this is just 2 on the square root of 8. Here is 4 times 2, so I want to kind of simplify this. The 4 is a perfect square, so I can take that out as a 2. So this would be 4 square root of 2. Okay, so number 7, number says evaluate h at negative 1. Okay, and this is pretty easy because this just is, well, what is h of x? H of x was just 2 over x plus 1. There's no building function. This is just the base function, the basic. Okay, and then h of negative 1 would be 2, negative 1 plus 1, 2 over 0. So this does not exist. Okay, this, if we did the domain, the natural domain would be negative infinity up to negative 1, union negative 1 to infinity. Because we had to pull out for x plus 1 equal to 0, negative 1, that's the number I have to pull out. Okay. So evaluate and write the domain in interval notation. So s of x is equal to 2 over x. You remember that graph when we did the basic one? This was like here. F of x is equal to 1 over x. This is just the basic function scaled by 2. So all of these things are going to tighten up because I'm multiplying them by 2. Okay, but here I'm not doing any shifts up and down, left, right. I've still got a problem where x is equal to 0. I can't have that. Okay, this, the line y is equal to 0. I'm sorry, x equal to 0, sorry. X equal to 0, all along this x equal to 0 line, that's the vertical asymptote. That's going to be called the vertical asymptote later on. Okay, so the interval 0 union 0 to infinity. That's the domain of S. Okay. So our quick review, t of x plus 4, all real numbers. Polynomials, negative infinity to infinity. There's no problem. Give me any number, I stick it into there, I add 4 to it, I get a number. That's okay. That's just that number shifted right by 4. Okay, so that is no problem, all real numbers. All the polynomials, remember p of x equal a to the n, x to the n, all the way down to a1 dot dot dot, a1x plus a0. Any of these, and this is just a straight line, which is just that end point. This is a first degree polynomial. Any of the polynomials nth degree, I multiply it by itself, multiply it by constants, add these things up. All of those are basic operations that are well-defined. I come out with a well-defined number. So anything like this, the domain of a poly is negative infinity to plus infinity. Okay, so t of x, negative infinity to infinity. It's a straight line. Give me an x, there it is. Okay, r of x. Okay, polynomial looks like that. The base function shifted up by 3. Remember our transformations, the base function being x squared and then up by 3. So a quick sketch, there's my 0, 3. And then it goes up, goes up. Okay, so all real numbers, polynomials. This is a second degree polynomial. 1 x squared plus my a0 is my 3. So this is down to x squared plus my a1x. My a1 is 0 to get rid of the x, and then I just got my 3. Domain of t, domain of r. And then finally it says r minus t of x. Evaluate this thing. Well, this is my r of x minus t of x x squared plus 3 in parentheses minus my t of x is x plus 4 in parentheses. So this is just x squared minus x plus 3 minus 4 is minus 1. Okay, minus x minus 4, and then I group. Okay, polynomial, domain, negative infinity to infinity. Okay, the domains, when I do these functions, it has to be a domain of both of these. Everything has to make sense. If I'd have done the 2 over x, if I'd have done the s of x, I would have to pull out that 0 again that we did, like right up here. Okay. So the domain, when I do this, it's got to work for both the original ones. Okay. Here's kind of the same thing. So here's the function m of x is negative the absolute value of x. Okay, So what does that look like in transformation land? Here's the base function, absolute value flipped around the x-axis. So that would be like that, okay? N of x is a constant function. It's just always 4 no matter what. And finally, it says form m plus n of x, which is, what does this mean? It means m of x plus n of x. And then I just fill this in. Negative absolute value of x plus my n of x is equal to 4. And there you go. The domain, all of x. This is all of x. That's all of x. No problem. In terms of transformations, what is that? That's that flipped and then up by 4. So I would kind of look at this as saying, here's the absolute value. I'm flipping it, working into out, and then I raise that by 4. So that would look like that. And this one would be 0, 4. Domain, negative infinity to infinity. Give me any number, I can take the absolute value of it, multiply it times negative 1, and then add 4. Here's some, so the very same, and it just says continue on, form, so here's A, form n minus n, and then evaluate at negative 6. So this is like a 2-step. I can also say, well, this is evaluate n at negative 6 minus m. In fact, we'll do that after we do the fundamental. So this is n of x minus m of x. This is now the 4 minus, and I want to make sure I do this, minus the absolute value of x. Because here I need to change sign. So this is 4 plus the absolute value of x, and then evaluate this at negative 6. So this is 4 plus the absolute value of negative 6. Absolute value of negative 6 is plus 6, outside plus 6. So this is just 10. Okay. Now let's see if we can do it from up here. Let's see if we can do n of negative 6 minus m of negative 6 and see what we get. N of negative 6, no matter what, this is always 4. And m of negative 6 would be negative, the absolute value of negative 6 plus 6. This would be did I do this right? Plus minus m of negative 6. So here, minus the negative 6 minus the m of negative 6 is my negative 6 is 6, negative 1. So that's negative 6 and then the minus, and then that gives me the very same thing as the 10. Same functions, new functions from old. We can do all the different combinations of these things. And B says form n times p and evaluate at 0. So my n times p of x, that's my 4, times my, oh, where's my p? I'm given a p. I'm assuming that this is n times m. I think the slides from McGraw-Hill kind of messed up on this. Let's do it this way. So n of x times my n of x minus the absolute value of x. And then once I've done this, minus 4 times the absolute value of x, then I evaluate it at 0. N times m of 0 is equal to absolute value of 0 is just 0 times negative 4, that would just be 0. And again, let's do that switch. N over m of 0. So let's form n over m of x. And that's n of x divided by mx, m of x. N of x is 4 divided by minus the square root of x. And if I would simplify this, I would either put it up out front or up top. And that's probably the way I would write it, just to save a little space instead of having that negative sign out there. Okay, so once I do this, though, if I'm forming this general function, I want to make sure the bottom piece is not equal to 0. So I want to exclude that domain. So where's the absolute value of x equal to 0? And the only place is going to be when x is equal to 0. So my domain makes sure 0 union 0 to infinity. And now it says to evaluate at 0. Well, that's not even in the domain. Does not exist. Okay. So let's do, let me see, we've done that one. Here's the P. Maybe this is the one that just got it out of thing. That was the P. Let's do a couple of these things. Because I want to kind of cover a couple of things. So let's do, here's m of x, x plus 3. Here was p of x, square root of x plus 1. What was the domain of m? That domain of p, this had to be greater than or equal to 0. So here, negative 1 to infinity. Okay. So before we ever start kind of do the domains, once we start getting into these things, and then no matter how we do it, whatever we form, I have to be the same thing. And so it has to work for both. So if I did m plus p of x, here's this domain. So this is all of this stuff. Plus infinity, minus infinity. I can get anything out of here, but this one has to be in here. And when I form any function with these, then I have to, my new domain has to be the intersection f, so this would be m, do the intersection of domain of p. So this is domain of p, this is domain of m, and this intersection thing says and. So it has to be able to satisfy both of these things, which would be the smallest, so it would be this, okay? So this would be of negative 1 to infinity. If I did the domain, so if I form this function, m over p of x. I've got to take the additional, so this has to hold, plus remove or p of x equal to 0, okay, because I'm doing that division, okay? So so this is just m of x divided by p of x, and you kind of see this as we go. M of x is the x plus 3 square root of x plus 1. So it says, oh, this can't be equal to 0. So where's all of this stuff in the bottom? Equal to 0, and then I do whatever it is to solve this that we've looked at. So here I would, if I squared both sides, I get x plus 1 is equal to 0. So x can't be equal to -1. So in this case, the domain of m quotient p would be just the -1 to infinity, not including the -1. So this, so let me do this piece of it. Okay. So this, I could be -1 when I forward m plus p. M plus p was just x plus 3 plus this. It would be okay. I can include the -1. This just kind of, I have to have that being greater than or equal to 0, but it can't be equal to 0 down here. So I had to pull that out. Okay, so let me do, instead of evaluating a difference quotient, I want to kind of give you a quick overview of composition because that's exactly what we're doing. Okay, so f of x is equal to, let's go x squared, g of x, let's do a simple one of like x plus 1, and then composition. F circle g. F circle g. Okay, so this is not times, and what this is the f is going to be on the outside. So if I take that function like here, but on the inside where the x is, I want to evaluate that at this. Okay, so for this, if I'm going to evaluate f circle g of x, I'm going to tell myself f is on the outside, here's my f function, but on the inside is my g of x. This is the second piece. Okay, and what does that look like? I build my f of x, so in this case, that's just that simple x squared. If I had other stuff, I'd just write it down. But now my g of x that goes, I evaluate this thing, is this stuff. So I need to evaluate x plus 1. That's the g of x. X squared plus 2x plus 1. Square the first, double the multiplication, and then square the last. Okay? Now, if I did this one, form g circle f of x, here, this is g on the outside, g on the outside, so here's my regular g of x, put the stuff of f of x in there. So it's a different, both of these things are not the same. So here, g is on the outside, so this is this plus 1, my x plus 1, and now I'm putting my f stuff on the inside of my parentheses. There's x. So this thing is equal to x squared plus 1. Okay, so that's the basics of composition. There's some other stuff we got to do, but we're going to do this when we evaluate the difference quotient. We're not going to do it exactly by using this term. We're just going to say evaluate a function at some stuff, okay, which is composition, okay? And to do that, we need to evaluate the difference quotient, okay? So basically, if I have a line, so I'm going to do this picture to kind of save some time on the lecture. I'm going to do the difference quotient, right? So it is the delta y, delta x, the rise over the run. But what I'm going to do is represent everything in terms of I'm going to do 1 point instead of 2 points. My second point is I'm going to add a little bit to the x, and I'm going to keep this as a parameter, if you would. I'm starting at just some arbitrary point x, moving over some h, and this is my second point, okay? So I'm starting at x, evaluate the function, that's f of x. My second point here is now I'm at x plus h, and I'm going to evaluate the function at f of x plus h. That's the height there. Here's the height at f of x at x plus h, and at x plus h, evaluate the function at x plus h. Okay, so if I do the rise over the run, my run is just x plus h minus x, which just simplifies to h. Okay, that's how far over we've moved. The function value has now increased to f of x plus h here, and I subtract off the original height to give me that delta height, or the delta y. Okay, this is the composition stuff, and here's basically my composition. Wherever you saw that x, put x plus h. Okay, so this thing is called the difference quotient. The dq. It is equal to, here's your formula, here's your cryptic math, and again, we write it to give you a math definition instead of every time going back over through all of this spiel. Here's your little cookbook of doing the difference quotient. Form the function f at x plus h, evaluate f at x plus h, subtract off the original function, divide by h, okay? And that's going to give me, and basically what that's going to be able to do, let me kind of draw a real quick picture. You remember where we said the average rate of change, where it all depended on the starting point and the ending point? What we're going to do now is always going to be this starting point, and now we're going to say, well, here's for a big H. What about if it was a smaller h? What about if it's a very, very small h? And for very small h going to 0, let me just get rid of this. I don't really need this. This is the slope of the tangent line. The tangent line just touches it at that point x. Okay, and it's going to be an arbitrary function, so we can, as a new function from an old stuff, and we'll be able to tell the slope anywhere along this lines in terms of x and the h. And in calculus land, when you take calculus, they're going to always shrink this thing to 0, so you don't even have any h's in there. Okay. So for right now, we need to learn how to evaluate this difference quotient. Okay. So I like to kind of break off and do some basics to kind of show you. So anytime, let's say if I had f of x is equal to, let's say, some straight line. So let's go through here. 2x plus 1, some basic thing. And if I do the dq, it says take f, evaluated x plus h, minus f of x, divide out the h. Okay? All straight lines are going to work out this way. Okay? So it says take the function and evaluate. So I'm going to do a little curly brace for this piece of it. Here's my function x. So you remember how I did that composition a while ago. Now where do you want me to evaluate it at? At x plus h. Close my curly. This is this piece of it. Minus, and I'm doing it with, instead of parentheses, because I've got parentheses where the x is. Minus f of x, that is just the 2x plus 1. That is just f of x. So subtract off the original. So this has gone through a change of height, okay? and then we're going to divide by h in just a second. Okay, so we're going to expand 2x plus 2h plus 1. This is all of that. This is a plus, so I get to drop all of these. But here, this is a minus, so I need to subtract off minus 2x minus 1 divided by h. That goes out. The originals will always go out. That f, this stuff, will always subtract off the original. Okay? This will always happen. Sometimes a little bit later, but for most of the functions of polys and everything, this is going to do right off the bat. So now you're going to, the top is always going to have h's in it. Okay? This is just simply 2h over h. Usually there's some canceling. You need to be able to cancel that stuff. And in here, I just come up with 2. But look at here. If I just did a mx plus b and did this thing, this would come out with whatever m that is. That is the slope. That's the m. The difference quotient is the slope. And in this case, it didn't matter what my starting point is. Wherever I'm at on that line, my slope is going to be 2. Okay, a constant slope. Anytime you do the difference quotient for mx plus b, you're going to get dq is equal to m. This very same process. Not very enlightening there. I agree. Now, again, I like to do some basic functions, and then we'll practice kind of in lab. But again, the difference quotient, and let's start out with f of x. Now, this could be g of x, z of x. I do the same thing. I just call it z, the z. But here is minus, do f of x equal x squared. I do a very simple one. And then I'm going to do the dq, the difference quotient. Not Dairy Queen, but difference quotient. F, x plus h. I always write this out as my first step. I remind myself what I'm doing. When you're doing it, you're reminding me of what you're doing. Okay? So now I take the original function. I'm going to do this minus this, okay, over h. This I'm putting here. This I'm putting back here. So this one's easy. It's always the original function. This I have to go through, replace with parentheses, and here I've only got a squared, and now I put my x plus h here. Okay. This is good. I can kind of drop that. My minus I don't have to distribute. This is all I've got to do is expand x squared, multiply the 2 together, xh doubled is plus 2xh. And then square the last, then subtract off the original, and there's my h. And again, simplify. The original stuff should always subtract off from here, and if it doesn't, you've got some signs wrong in there. Okay. Everything left should have some h's. You can treat this as this divides into each everything, or I factor out an h and then cancel from above, okay? So if I factor out the h, I get h, 2x plus h, divided by h, and that's just left my 2x plus h. So it says, give me the x, the starting point, how far away, and that's the slope between those 2 points. Okay, and again, in Calc 1, you're going to say, just make h smaller, smaller, smaller until that's 0. I can't do it to start with because I can't divide by 0. So this process is called the limit process. The limit as h goes to 0, you may have seen that earlier, and that's what that means. So this, if I shrunk this thing, all I'm worried about is the 2x. And in calculus, in Calc 1, that would be called the first derivative, is doing this process. There's some formulas. Take this, multiply, subtract 1, 2x, subtract 1, 2x, 1, 2x, 1. Okay. So there's some easier ways as you go forward, but right now we're kind of developing that basic thing. Okay, so there's that one. Again, if I'm just doing it with anything, I just need to be careful. Let me do a bigger one, and then I want to do two more to give you the basics of what that would have to do. So if I've got f of x equals to x squared minus 3x plus 8. And if I do the dq, again, that's f of x plus h minus f of x all over h. That's the standard definition we start with. Squiggly, squiggly, all of that stuff needs to go in here. I need to open it up. And then squiggly, squiggly, okay? All over h. So this is x plus h squared minus 3x plus h plus 8. And then the original looks like x squared minus 3x plus 8. Okay? And then I just expand, group, and simplify, and this is what this would look like. Again, that would just be the x squared plus 2xh plus h squared minus my 3x minus 3h minus 3x minus h plus 8. And then I want to subtract off my x squared, so minus x squared plus 3x minus 8. And everything here, negative x squared with plus x squared, that goes out. Plus 3x minus 3x, that goes out. Negative 8 plus 8, that goes out. The original function has been subtracted out. Everything else, so this is my checkpoint, everything else should have an h in it. And then this divides into here. So this looks like, let me write it like it's supposed to, h squared plus 2xh minus 3h. And then I divide out a h from each one of them, or factor out the h. H plus 2x minus 3. Okay. Either way, I'm going to get the h plus 2x and then divide that out minus 3. And I usually write this, for me, the h at the very end, because our next step in calc or whatever would shrink this to 0, make it as small as what we can, make it insignificant that we could toss it and just have our difference quotient just being this thing. And that's a new function. That is a new function from an old, and in calculus, they just call this a prime function. I started with one thing. I could call this different out, dq of x or something, but that's what they usually do. Okay. We'll work on some more of those in lab. Let's go through composing and decomposing function. Here's what I told you before, the F circle G. This is the composition. F circle G is composition. The first one is my outside function, and then I put the stuff on the inside. So this, just a minute ago, we used x plus h and just did that directly, but that was what we were forming as a composite function. Okay. So here is f of x, x squared minus 3x plus 1. Here's our g of x, 5x plus 4. And it says form these two things, f circle g of x, okay? So every time I go and rewrite this, what does this mean? Because it gives me the rules that I follow after that. And I have to remember this is f on the outside. The first one I go is this, the first one here. But then on the inside, I'm evaluating f when x is this, the g of x, okay? So this is, I start with my original function. This one tells me which one I start with. So my outside, this is my outside. Something squared, the number squared, minus 3 times the number plus 1. Give me the number, right? And that was just x was just a placeholder, right? You had to wait around for whatever this x is. But here, now it's saying the number is g of x. Now it is a function of x. So in here, I put my g of x, minus 3, 5x plus 4. So this is g of x squared minus 3 times g of x plus 1. And then I just simplify, square the first one, multiply the two together. 4 times 5x is 20x, doubled it would be what, 40x. Square the last one, the 4 squared is my 16. And then I do this like I did a while ago, minus 15x minus 12 plus 1. And then I would simplify. This is the big thing right here. You'll get better at the simplification as you go through and continue and continue and continue. To me, this is the most important part of all of this, is to understand the composition part, putting it where it needs to be, evaluating each one. This is kind of secondary. It's kind of like, here's your algebra. Your algebra is going to prove just for about being conscious of it. And I would kind of go through and group 40x minus 15x is what? 25x plus 25x. That one goes out, that one. 16 minus 12 is 4, and then plus my 4 is 8, if I did that part right. What did I do 4 here? The plus 1, I'm sorry. So that was the 4, and here was plus 1. So I need to go back over here. 16 minus 12 is my 4 plus 1. That needs to be plus 5. Sorry. I was thinking that 4. I thought I miswrote that one. Okay, so that's the concept of a F circle G. What about if I do G circle F? That is not the same thing. These two are in general not equal. Okay, later on we're going to see an example of where they are equal, but in general they're not. G on the outside, F of x on the inside. So what's my G? This is equal to 5, my parentheses for my x plus 4. Okay, and now I evaluate this at F of x. X squared minus 3x plus 1. Okay, and then I just do regular algebra after that. 5x squared minus 15x plus 5 plus 4. And that's that basic, so this is not the same thing as what we got up here. Okay. So we'll work on some of those more later. We'll go through here. So in many cases, it would be helpful if we could break these things apart. I've got a complex function, okay? This isn't it here, though. Here. So I want to cover real quick decomposition. And this just kind of takes a little look back. There's no formal rule for it. It's sit back and look and see if you can find some base functions. Do you remember when we did the original, when we were doing transformations, we found some base function? This is the very same thing. Remember when we did f of x is equal to square root of x minus 1. We do this, okay, here's a base function. We know what that graph looks like, and then we do transformations. This is a very similar thing, but we're kind of looking backwards as decomposition. So if I have this, think of this stuff as, well, what would if I started with, and if I was doing transformations, what would that look like? Well, the base function is just x cubed, right? I see, here's the biggest thing I see is some cubic function. Okay, and then I would say shift left by 1 up by 8. But here I want to consider a composition, two functions. So I want to start with 1 plus 8. And then my g of x would be my x plus 1. Okay? And in this case, if I did f circle g, and this is what this piece of it, so I'm forming h of x, which is this thing, f of x, f of g of x, f on the outside, g on the inside. My f is this, g is on the inside, and that's this thing. I've decomposed my h into these two things, and that's decomposition.